La enorme gama de sonidos humanos es producto de un sistema exquisitamente complejo. El sentido de las palabras, la estética de las canciones, pueden ser alterados por diminutos movimientos en los que participan el diafragma, los pulmones, la tráquea, la boca, la nariz, la lengua, los labios y los dientes. El solo sonido creado por las cuerdas vocales es simple y débil. Dentro del oído, el sonido hace vibrar al tambor, proceso visto aquí 200 veces más lentamente. 3 diminutos huesos hacen pasar las vibraciones para convertirlas en impulsos eléctricos recibidos por el cerebro. El músculo del tímpano protege al delicado aparato contra el ruido excesivo. Viendo moverse al músculo, podemos apreciar cómo escucha el oído.
En un oído normal, las ondas sónicas entran por el canal auditivo externo, golpean el tímpano y lo hacen vibrar, lo cual hace vibrar a 3 pequeños huesos del oído. El último, llamado estribo, empuja el fluido en el oído interno. El oído interno tiene pequeñas células ciliadas que son estimuladas por los cambios de presión del líquido en el oído interno. Y esas células ciliadas inician una corriente eléctrica que fluye hacia el nervio auditivo, el cual transmite los impulsos eléctricos al cerebro y entonces oye.
En 1940 se derrumbó un puente suspendido de reciente construcción en Tacoma Narrows, Estados Unidos de América. A la hora de diseñar el puente no se había estudiado adecuadamente el efecto de la resonancia. Las vibraciones del viento coincidieron con las naturales del hormigón y se produjo el fenómeno de resonancia. Esta hizo aumentar el balanceo del puente hasta que se derrumbó en las aguas del río.
El sonido empieza en una fuente de vibración que hace que las ondas viajen por el aire como olas sobre el agua. Las ondas crean un patrón en las moléculas del aire circundante. En el frente de la onda, las moléculas son empujadas juntas, las de atrás son separadas. Estos patrones de ondas se mueven hacia afuera desde la fuente con las ondas más fuertes sonando más intensas que las débiles. Una frecuencia sónica o valor hertziano es el número de ondas que pasan un punto determinado durante un segundo. Mientras más ondas por segundo, más agudo es el sonido. Algunas criaturas oyen tonos tan agudos o tan graves que están fuera del rango del oído humano.
Everything in nature is made up of vibrations, waves, periodicity, and all wave phenomenon follow basically the same rules. As waves move out from their point of origin, their energy is dissipated. When they strike something, they reflect and cause interference with subsequent waves. Sound is a pressure wave, an undulating sphere of changing atmospheric pressure, moving out in all directions from a vibrating source. If some point is described as a relaxed, neutral position, a wave will have a positive excursion or compression of the atmosphere and a negative excursion or rarefaction of the atmosphere. When the wave strikes a sensitive surface, like the diaphragm inside of a human ear or the diaphragm inside of a microphone, the fluctuations in atmospheric pressure create a corresponding vibration in the diaphragm. The microphone uses the vibration of the diaphragm to create a fluctuating electronic signal. Right now, you're looking at the signal produced by my voice. Once amplified, that signal can be used to vibrate the diaphragm of a speaker, which in turn creates the atmospheric pressure waves that we hear as sound. Reality sound is definitely not a simple wave. But for the sake of description, that's what we'll be using. This is a sine wave. We have a signal generator hooked up to an oscilloscope, and we can both see and hear the tone. The frequency of the signal is the number of complete cycles that occur in a given amount of time. This is usually described as cycles per second. As the cycles per second increase, so does the pitch. A wavelength is the physical space occupied by one complete cycle. On Earth, sound travels about 1,100 feet per second, with some variation depending on altitude and temperature. So, this 1,000 cycle tone has a wavelength of little over 1 foot in reality space. Here on the scope, that wavelength is compressed so that we can observe it. The amplitude of the wave is how loud it is. Basically, the higher the wave goes above or below the median, the louder the signal will be. In the case of acoustic power, it is the amount of sound pressure variation above or below the prevailing atmospheric pressure. In the case of an electronic signal, it is so many volts above or below the median voltage. Now, the average median voltage, or ground plane of an electronic circuit, is halfway between the positive peaks and the negative peaks. When the signal rises above the median, the speaker cone is pushed outward, and when it goes below the median, the speaker cone is pulled inward. Zero level is a point which the designers of a system, for instance a console or tape recorder, have chosen as the average maximum operating level of the system, though allowances have been made for occasional signals of greater magnitude. The strength of the signal is measured in decibels, a unit of sound measurement, above or below this average operating level. Headroom is the dynamic range between the average operating level of a system and the level at which severe distortion will take place. Clipping is what happens when the loudest peaks of the signal bump against the ceiling of the amplifier. The peaks are flattened or distorted.
Let's look inside a typical dynamic microphone. Inside is a diaphragm, like the diaphragm inside a human ear. As you can see, it moves freely in response to pressure. Like a weatherman's barometer, the diaphragm responds to slight atmospheric pressure changes on its surface. Obviously, a microphone, like our eardrum, is significantly more sensitive in its ability to pick up slight and rapid atmospheric changes. Moving coil, or dynamic microphones, are designed along the lines of a speaker. A moving coil microphone has a spooled coil connected to its diaphragm, usually at the back. The coil sits inside of a circularly channeled magnet. As the diaphragm moves inward, the coil breaks magnetic lines of force spanning the gap in the magnet, and a current is generated in the winding. When the diaphragm moves outward, the magnetic lines of force are broken from the opposite direction, and the flow of current in the coil is also reversed. The oscillating voltage electrically shadows the acoustic sound. How often the diaphragm changes direction reflects the frequency or pitch. How far the diaphragm travels in a given instant reflects the loudness of the sound and determines how great the output voltage will be during that instant. Length is the physical space occupied by one complete cycle of a given frequency. For example, a 1,000 cycle tone has a wavelength of about 1 foot in reality space. If the distances involved between a direct sound and a reflected sound are about the same as the wavelengths of the frequencies being played, the two signals will add and subtract from one another, according to the phase relationships of each frequency present. In this case, the sound bouncing off the wall reaches the mic 1/2 cycle after the direct sound and cancels it out with an equal but opposite pressure. In this example, the microphone is picking up a direct signal from the speaker and a reflected signal from the wall. At certain distances, these two signals will audibly cancel one another. Phase cancellation will be greatest when the delayed signal is half a wavelength after the undelayed signal. In this example, two microphones are picking up a 1,000 cycle tone, and you're seeing the combined signal on the scope. Since a 1,000 cycle tone has a wavelength of about 1 foot,
The greatest cancellation between these two mics occurs when one is 6 inches further from the source. Cancellation of a lesser degree occurs at 1.5 wavelengths of delay, 2.5, and so on, each cancellation creating a dip in the frequency response. This is called comb filtering, because a group of narrow notches form what appears to be a comb in an otherwise flat response curve.